What's up, guys? In this video I'm going to show you how to
Let's start with this problem. Find the mean, median, mode, and range of the following dataset. Now, the first thing that I would recommend doing is arranging the numbers in increasing order. So the lowest number is 7. In this video, we're going to talk about how to calculate the probability of a binomial distribution. So here we have a problem where a 6-sided die is rolled 12 times. Now, how would you answer this question? What is the probability of getting the first 6 on the 4th row using a 6-sided die? You need to realize that this is a geometric distribution. You're trying to find a probability that a successful event will occur on the 4th try. So during the first row, you're going to get a failed event. During the second row, it's another fail. But during the 4th try, you're going to get a successful event. Third divided by 1, probability Q is a probability of not getting a 6, which we said is 5 over 6. And a 6 and goes at, we want to get a successful event on the 10th trial. Now let's write the formula. So let's replace little x with 10. Q is 0.96. 10 minus 1 is 9. And P is 0.04. So let's start with the mean. The mean is 1 over P. So it's going to be 1 over 0.04. And that is 25. Now what about the variance? There's a simple formula that we could use to calculate it. So that's for this problem. That's how you can calculate the mean, variance, and the standard deviation. Number 4, 2% of all tires produced by company XYZ has a defect. A random sample of 100 tires is tested for quality assurance. What is the probability that the 8th tire selected has a defect? So go ahead and take a minute and try this problem. So let's write down what we know. So what are the values of P, Q, and X in this problem? Well, 2% of all tires has a defect. So P is 0.02. That's the probability of selecting a defective tire. The probability of not selecting a defective tire is going to be 1 minus 0.02, which is 0.98. Now, in part A, we want to calculate the probability that the 8th tire selected has a defect. So X is 8 for part A. So let's write the formula. So we need to find the probability that X is equal to X minus 8 is less than or equal to 5. So
probability of X is equal to 5. Minus 1 minus.
When X is 2, all the way, and X is 1, X plus to the point of product. So yes, it's going to Q to the 3rd, P to the 1st. And when I'm confused in terms of formula. Now, it's 20 simpler function. So in this case, little x is 5. So this is going to be 1 minus 0.98 raised to the 5th power. So go ahead and type that in. This will give you the same answer of 0.09607. So make sure to add that formula to your list of other formulas that you need to know. So now that we have this formula, we can use it to calculate the answer in part C. What is the probability that the first defect is detected among the first 10 samples? So this is going to be P.
So that is p x less than or equals to 10, which equals to 1 minus what is
of x is less than or equal to 10, using this formula again, it's going to be 1 minus 0.98 raised to the 10th power. And so the answer is going to be 0.182927. So that's approximately an 8.3% chance that the first defect will be detected among the first 10 samples. Now, what about part D? How many tires would you expect to test until you find the first defective one? How can we find the answer to that question? So go ahead and think about it for a minute. Pause the video if you will.
so it's just 1 over p. That's 1 over 1 over
The answer is the mean. All we need to do is calculate the mean, and that's going to determine the number of tires we expect to test until we find at least one defective one. Number 5. 2% of all tires produced by company XYZ has a defect. A random sample of 100 tires is tested for quality assurance. Calculate the following. So go ahead and try these problems. It's based on a previous problem. So what is the probability that x is less than 7? What is the probability that we're going to find a defective tire within the first 6 samples? So keep in mind, p of x, which is less than 7, this includes all the numbers from 1 to 6. It does not include 7. So how do we get this answer? Now, remember the formula that we used before. P of x less than little x is 1 minus q to the x. So right now, we have the less than symbol, but not the less than or equal to symbol. However, we can turn this expression into something like this, because this is 1 to 6. So we could say that P of x less than 7 is equivalent to P of x, which is less than or equal to 6. So now we can use this formula. So this is going to be 1 minus, now keep in mind Q is still 0.98 and P is 0.02. So this is 1 minus 0.98 raised to the 6th power. And that is going to be 0.11416. So there is approximately an 11.4% chance that a defective tire will be identified within the first 6 samples. Now, let's move on to part B. So what is the probability that a defective tire will be found, let's say, beyond x is greater than 12? What formula can we use to calculate this particular probability? Let's draw a picture. So this is the shape of a geometric distribution. We have the probability on the y-axis, the random variable x on the x-axis. Now this is going to range from 0 to infinity. But for this problem, our focus is 12. This region here, let's separate it into 2 parts. The region on the left represents the probability. This is range. We have so the probability that x is greater. So now we could use that to get the answer for part B. So this is going to be 0.98 raised to the 12th power. Which is 0.78472. So there's a 78.5% chance, approximately, that a defect will be found beyond the 12th sample. So the defect will be found between sample 13 to sample infinity. Now let's move on to part C. So what is the probability that the defect will be found from sample 18 to sample infinity, or x is greater than or equal to 18? So we're going to use this formula again, but we need to change it into this form. So this is between 18 to infinity. So we could say that we're looking for the probability that x is everything beyond 2, finding a defect. Now, let's read for standard 4. So let's rearrange the equation to solve for this expression, which means these two expressions we need to move to the other side. So I'm going to erase this picture at this point. So we could say that the probability of finding a defective tire from sample 15 to sample 30 is going to be 1 minus p of x is less than 14 minus p x is greater than 31. Now let's get rid of this. And let's focus on calculating these two values first. So 1, it's going to be. So this is the same as x is greater than 30, because that would still be 31 to infinity. So we're going to use this formula to the this is what I'm probability of the probability that x is, and that's 1. In this video, we're going to talk about how to use the Poisson distribution formula in order to solve problems. So take this problem, for example. A small business receives, on average, 12 customers per day. What is the probability that the business will receive exactly 8 customers in one day? So the first thing you want to keep in mind is that the time interval is the same. It doesn't change. So thus the mean is 12 customers per day, or the average. Now some textbooks will use lambda for the mean. mean. I'm going to use this symbol here. U per day, or the average. Now, some textbooks will use lambda for the mean. I'm going to use this symbol here. Now, to calculate the probability, we're going to use this formula. Capital X is the random variable. Lowercase x, in this case, is 8. That's the probability that we're trying to calculate. We want to know what's the probability that the business will receive exactly 8 customers in one day. So x is 8. And the formula is mu raised to the x, e to the negative mu, divided by x factorial. So let's replace lowercase x with 8. So this is going to be 12 raised to the 8 e to the negative 12 divided by 8 factorial. Now, keep in mind e is the inverse of the natural log function, and e is basically a number. It's 2.71828. 8 factorial, that's 8 times 7 times 6 times 5, all the way to 1. So if you were to plug this into your calculator, you should get, hold on one second. You should get 0.065523, which if we multiply that by 100%, that's approximately 6.55%. So that's the probability that this business will receive exactly 8 customers in one day. Number 2, a student receives, on average, 7 text messages in a 2-hour period. What is the probability that the student will receive exactly 9 text messages in a 2-hour period? So what do you think we have to do in order to solve this problem? Go ahead and try it. Now, there's something that you need to pay attention to, and it's the time interval. Notice that the time interval, it doesn't change. It's the same. So therefore, 7 is the mean. Now, the only other thing that we need to find is x. We can clearly see that x is 9 because we want to calculate the probability that the student will receive exactly 9 text messages in that 2-hour period. So we need to calculate p when x is 9. So let's go ahead and plug everything in. First, let's write the formula. So as we said before, it's mu raised to the x, e raised to the negative mu, divided by x factorial. So x is 9, mu is 7. So this is going to be 7 to the 9th power, e raised to the negative 7, divided by 9 factorial. So let's type that in. Of course, make it in mean by 4. Now, sometimes you could set up a proportion over 28. Mean form. So therefore, you need to multiply the mean by 4, which will give you 28. 7 times 4 is 28. So that's the new mean value. Now, sometimes the math will not work out as nicely as what we see here. So you could set up a proportion. If you want a formula to do this, you can use this one. Mu2 over mu1 is going to be mu. Now, let's rewrite what x is going to use that is 0. Number, what is the probability that the business
It's close. It goes below. It goes very close. So basically, lambda x. It goes. It goes. It goes. It goes by half. It goes. It goes by lambda x. It's by 7 multiplied by it's by minus 8. So back to the so assuming is probability of x equals to x equals to lambda x e raised to power minus lambda over x factorial. Probability of x is equals to x. So more than. So there is no matter.
Will receive see that the so x it so this is equal all the time. Of doing u to the x, the u right equal to 5 is going to these values when x 0 plus the x-axis split in 30% will be greater than 1 if because these side this front. In this video, we're going to talk about the difference between continuous data and discrete data. Now, continuous data is data that can take on any value in an interval, whereas discrete data, it can only have specific values. So let me give an example. So let's say we have the interval 1 to 10, or we can write it this way. Let's say that x is a value between 1 and 10. Now, in a continuous set of data, x could be 1, it could be 1.3, it could be 2.46, it could be 5.389. It could be any value between 1 and 10. Now, on the right side, when dealing with a discrete set of data, x can only have specific values. For example, it may only have values that are whole numbers. Such as 1, 2, 3, 4, 5, and so forth. So here it only has specific values, not values like 3.46 or 4.785. Now, so if discrete data natural numbers is data that can be measured. Now, continuous data is data that can be measured. So if you're measuring something, it's not only going to be whole numbers, it can be decimal numbers or fractions. Discrete data is data that is counted, and it's very easy to count whole numbers and natural numbers. So a good example of continuous data would be, let's say, temperature, because you can measure the temperature on any given day. For instance, today it might be 83.6 degrees Fahrenheit, or tomorrow, let's say that 3, 4, 5, or 6. If you roll a six-sided die, you can't get 2.37 or 4.6 because it can only take on over. It represents a continuous set of data or a discrete set of data. Let's start with number.
The number of cards. Sorry. The speed of a car is actually like continuous, discrete, 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 continuous, discrete, continuous.
Number one is that a. Now, what about your pounds and weight? The number of doctors in doc can be calculated with problems deal with your age. The age is number or nothing. 20 years old. So talk about continuous or if it represents age data. Now, the next thing we're going to talk about are graphs, because you need to be able to distinguish if a graph is continuous or if it represents a discrete set of data. So I'm going to draw a few pictures. And as I draw these graphs, go ahead and pause the video, or while I draw, just determine if it represents a continuous set of data or a discrete set of data. Looking at the first one on the top left, would you say it's continuous or discrete? For it to be continuous, there can't be no discontinuities, no jumps in the graphs. Basically, it's going to be a straight line. Well, not necessarily a straight line, but a connected line. All the data in this graph is connected, so this would be continuous. The second example will be discrete. You can easily tell it because it's going to be discrete. And so that's a quick and simple way to display it. In this video, we're going to talk about continuous probability distributions. So here's an example of a type of continuous probability distribution. This one is called the normal distribution.
It's normal distribution.
Now it has the continuous random variable x. X could be anything. It could be 2, it could be 3.5, it could be 4.68. It could be anything along the x-axis. Now, if we had discrete random variables, x would have restrictions. It could be like 1, 2, 3, 4, 5. But when dealing with continuous random variables, x could be anything. It could take on any value. Now, on the y-axis, we have the function f of x, which is also known as the PDF, which stands for the probability density function. Now, f of x will tell us the height of the curve above the x-axis at some point x. So f of x will give us the distance between these 2 points. Now let's put some letters here. Let's call this A, B, C, and D. We're going to use that shortly, but one thing I do want to mention is that the total area under the curve for a continuous probability distribution is always equal to 1. So the area of the shaded region, highlighted in blue, that's equal to 1. So I'm going to write TA for total area. That's 1. Let's say if we wish to calculate the probability that x is less than a. How would you do it? What you need to do is calculate the less than a. How would you do it? What you need to do is calculate the area under the curve of everything to the left of a. So it's going to be the area of the region shaded in red. Likewise, if we wish to calculate the probability that x is between b and c, what we need to do is we need to determine the area under the curve between b and c. Likewise, if we wish to calculate the probability that x is greater than d, we need to calculate the area under the curve to the right of d. So the probability is always equal to the area under the curve when dealing with a continuous probability distribution function. And keep in mind that f of x is always positive. It's greater than or equal to 0 for all x. So for a continuous probability distribution, you won't see the curve under the x-axis. It's always above the x-axis. Now, here's a question for you. What is the probability that x is equal to b? What would you say? Now, here we don't have a range of values. We simply have just the line at b. And for a line like that, the area is 0 because there's no width. You only have height but no width. If you try to calculate the area of a rectangle that only has height but no width, it's nothing. So whenever you try to calculate the area of a finite point, it's going to be 0. The only way you're going to get a value above 0 is x has to have a range of values. It can't have a single value. So just keep that in mind. Now, another thing that you want to keep in mind, let's say if you wish to calculate the probability that x is less than a. This is the same as the probability that x is less than or equal to a, because the probability that x is equal to a is 0. So less than or less than and equal to, it's going to be the same. So let's say if we want to calculate the probability that x is between b and c, this is the same as the probability that x is equal to or greater than b, but less than or equal to c. So those are some other things that you want to keep in mind when dealing with continuous probability distribution functions. Now, we briefly talked about the shape of the normal distribution. There are some other continuous probability distributions you need to be familiar with. The next one is the uniform distribution. The uniform distribution has a constant f of x value, as you can see.
This is f of x. This is x, right? This is PDF. It's in the height. Where the area is basically area under the curve. X less than x. This x.
And it ranges from A to B. Now, the area of the curve under the uniform distribution, or basically the area of the rectangle, is going to be 1. So let's say we have a uniform distribution from, let's say, 2 to 6. So A is 2, B is 6. If the area of the rectangle is 1, what is f of x? What is the value that corresponds to that point? If the area of the rectangle is 1, what is f of x? What is the value that corresponds to that point? Well, we know the base of the rectangle is 4. 4 times what number is 1? Because the area has to be 1. It's going to be 1 over 4. So that is going to be the value of f of x for this problem, for uniform distribution. Because if you multiply 1/4 by 4, you're going to get an area of 1. And so for any uniform distribution, the area under the curve has to be 1. So just keep that in mind. So now I want to give you some formulas that you need to know when dealing with the uniform distribution. So for uniform distribution from A to B, x will vary between A and B. The probability density function f of x is simply 1 over b minus a. In the last example, if you were to plug in a and b, where b is 6, a is 2, you would get the function f of x is 1 over 4. So that's how you would incorporate this formula to calculate the probability density function for a uniform distribution. Now the next thing you need to know is that the mean is equal to the average of a and b. So it's the sum of a and b divided by 2. And x is a standard deviation. That looks like theta, but it should be sigma. The standard deviation is the difference between b minus a divided by the square root of 12. So those are some formulas that you may want to write down when dealing with the uniform distribution, which is one of the types of continuous probability distributions that you need to know. Now, the next distribution that we're going to talk about is known as the exponential distribution. This is another continuous probability distribution that you want to add to your list. So it has a y-intercept, and then the function decreases over time, or with x. We have f of x on the y-axis, and the y-intercept is lambda, the rate parameter. The probability density function is f of x is equal to lambda e to the negative lambda times x. Lambda, the rate parameter, is 1 divided by the mean. So those are some things that you want to know for this type of function. And keep in mind the total area under the curve for this one or any type of continuous probability distribution function is always going to be 1. I had to erase it. A few things, but let's say if we have this point x, and we wish to calculate the probability that x is less than x. So that is the area shaded in blue. The formula for that, to calculate the area under the curve of that region, it's going to be 1 minus e to the negative lambda times x. Now, if we want to calculate the probability that x is greater than x, it's simply e to the negative lambda times x. In this case, that would represent the region under the curve to the right. So those are some other formulas that you want to know if you need to calculate the probability or the area under the curve. In this video, we're going to talk about cumulative distribution functions. And And keep in mind the total area under the curve. For this one or any type of continuous probability distribution function, it's always going to be 1. I had to erase a few things to calculate the probability that x is less than x. For that, this is at the right. So those are some other formulas that the region under the curve times x. In this case, that would represent the region under the curve to the right. So those are some other formulas that you want to know if you need to calculate the probability or the area under the curve. In this video, we're going to talk about cumulative distribution functions. The cumulative distribution function, or CDF, these functions are used to calculate the area under the curve, specifically the area to the left of some point of interest. Now these functions, they're used to calculate the accumulated probability. Now keep in mind, whenever you have a continuous probability distribution, the probability is equal to the area under the curve. And since the maximum probability is 1, the total area under the curve will be 1 as well. Now, probability density functions are different from cumulative distribution functions. The PDF, or probability density function, is f of x, and it tells you the shape of the distribution. So for instance, let's say if we have a uniform distribution. In this case, f of x will equal a specific number. It's going to be a constant value. F of x is going to be 1 over b minus a for a uniform distribution. It's a number. It doesn't have the variable x in it. You'll see something that looks like this. So this is f of x, and it varies from a to b. So this right here is the PDF. That is the probability density function for a uniform distribution. It's equal to f of x. Now the CDF the cumulative distribution function will give us the area under the curve to the left. So let's say the point of interest is x. The CDF will give us the area to the left of x, so the area of the shaded region in blue. Now, this is basically the shape of a rectangle. The area of a rectangle is the base times the height. Notice that the base is the difference between x and a. So it's x minus a. The height is f of x. And f of x is what we see here, b minus a. So the CDF, the cumulative distribution function, will give us the area to the left. So we have this formula. The probability that the random variable capital X is less than or equal to some number is going to be x minus a over b minus a. So this function right here, highlighted in blue, this is the CDF. That is the cumulative distribution function for a uniform distribution. It gives us the area to the left of some value x. And the PDF is just f of x. For uniform distribution, that's 1 over b minus a. Now, let's talk about the exponential distribution. Let's discuss the CDF and the PDF for this type of distribution. The exponential distribution, the maximum value is the y-intercept, and it decreases over time. The maximum value is also known as lambda, the rate parameter. The probability density function for an exponential distribution is going to be the function f of x, which describes the shape of the distribution. And f of x for this particular distribution is lambda e to the negative lambda times x. And lambda is the rate parameter. It's 1 divided by the mean. So this is the probability density function. It tells you the shape of the graph. That's what it does. In addition, it also gives you the height of the curve above the x-axis at some point x. That's another thing that it tells you. Now, the CDF gives us the area under the curve to the left of some value x. So let's say if we wish to calculate the area to the left. So that's going to be AL. That's going to be the probability that x is less than or equal to some value. And that's going to be equal to 1 minus e to the negative lambda times x. So that is the cumulative distribution function. It gives us the area under the curve to the left. So if we wish to calculate the probability that x is between 0 to x, or let's say 0 to a, this function will help us to get the probability. It's equal to the area under the curve. Now, what if we wish to calculate the area to the right, as opposed to the area to the left? We know that the total area is 1. So the area to the right plus area to e distribute the next to negative lambda times x. Simply e, because it doesn't give us the area to the left. It gives us the area to the right. So the CDF is what we see here. That's the CDF for an exponential distribution. Now, let's say if we still have an exponential distribution, but we want to calculate the area between a and b. So we want to find a probability that x is somewhere between a and b. How can we calculate the area under the curve? between those 2 points. Blue. This is like A. The problem we can replace that value with we can find the area to the left. So this is the distribution that you want to know with in the PDF and the CD. In this video, we're going to focus on uniform distribution probability problems. And so we have an example problem to start right here. Number one, in this video, we're going to go over the standard normal distribution, as well as some equations that you need to be familiar with. After that, we're going to work on some problems so you can see how to put these formulas to good use. So the normal distribution has... In this video, we're going to focus on uniform distribution probability problem. problems. And so we have an example problem to start right here. Number 1. The amount of time a person must wait for a train to arrive in a certain town is uniformly distributed between 0 and 40 minutes. Part A. Determine the probability density function f of x. between the rectangle. It's probability part A. We need to determine what the values for A and B are. It's simply, so we're going to draw a whole in 8 minutes. What do you think the answer is to that problem? So what is the probability that x is less than 8 over 40? What is that? Let's wait 1 over 40, 8 of 30. Go. What is the probability that a person must wait more than 30 minutes? And try that. You could say that you will have this 10 over 40. If you cancel a 0, or the probability. So what is the area of that? Again, area is going to notice that there is no rectangle for line. Therefore, the area about, let's say if x is equal to 35, I need to, where x is going to be 0. Now, what about the next one? Where time 10, it's see a problem where x is equal to a number. Let's say if x is equal to 35 or 15, it's always going to be 0. Unless you have an interval values or two different x values, like this one. If you don't have it, it's going to be 0. Now, the probability that x is greater than 45. If we were to extend this graph, 45 would be somewhere here. But notice that f of x is 0 beyond 40. So if you were to try to use the formula, base times height, your base could extend to infinity, but your height is 0. So basically, you have no rectangle. So if your height is 0, the area is going to be 0. Therefore, the probability that x is greater than 45, because it's outside of the range of 0 to 40, the probability is going to be 0. So that's the answer for that one. Now, let's move on to part F. This is A20. So you can round that to 11.5 if you want to. So that's how you can calculate the standard deviation for this problem. Now, what is the 85th percentile? Feel free to pause the video and try it if you want to. It's at the 75th percentile. 30 is the percentile. So the height is still the same. That's 1 over 40. K, and then times 1 over 40. To get rid of the fraction, we can multiply. A minus 0 is simply k, and then times 1 over 40. To get rid of the fraction, we can multiply both sides by 40. So the 40s will cancel on the right side. And thus k is simply 40 times 0.85. So because 85th percentile, now 84 is because of a percent practice. Let's try another example. You could work on it if you want to. Go ahead and pause the video to complete. 120 is now between. So go ahead and 1. So the probability is divided by distance. This is the phrase now that we're going to call it k. So the area of the rectangle to the left of k is 0.75 because it corresponds to the 75th percentile. So the area of that rectangle on the left is going to be the base times the height. So the area is 0.75. The base, the length of the base of the rectangle, is the difference between k and 20. So we're going to say k minus 20. And as we know, the height is f of x, the probability density function, which is 1 over 25. So now we need to do some algebra. Let's begin by getting rid of this fraction by multiplying both sides by 25. So these will cancel. So 25 times 0.75 is 18.75. And so we're left with this on the right side, which is k minus 20. The last step is to add 20. And this is the third quartile, 50th percentile. We need to do quartile, and we're going to call it k. So the area of the rectangle to the left of k is 0.75 because it corresponds to the 75th percentile. So the area of that rectangle on the left is going to be the base times the height. So the area is 0.75. The base, the length of the base of the rectangle, is the difference between k and 20. So we're going to say k minus 20. And as we know, the height is f of x, the probability density function, which is 1 over 25. So now we need to do some algebra. Let's begin by getting rid of this fraction times this on sides. It can be 38. As we can see, the numbers, 7.5. Let's move on to the last part, part G. What is the probability that the student will take more than 40 minutes to complete the test, given that he always takes more than 30 minutes to complete any chemistry test? So we have the keyword given. Go ahead and try this problem. So first, we need to recognize that we need to calculate a conditional probability. The formula for conditional probability, let's say if we want to find a probability that event A occurs, given that event B has already occurred, this is the probability of getting A and B. This is the intersection between A and B, divided by the probability of event B occurring. So in terms of this problem, we want to find the probability that x is greater than 40, given that x is already greater than 30. So it turns out that this is equal to the probability that x is greater than 40 divided by the probability that x is greater than 30. And let's talk about why that's the case. Now, looking at the first formula, we can illustrate this with a Venn diagram. Let's say A is on the left, B is on the right. So where the two circles overlap, that is the intersection of A and B. So the probability that A will occur, given that B has already occurred, is basically the area of this portion, that is represented between the base and the height probability. The lifespan of each laptop follows an exponential distribution. Part A, calculate the rate parameter. The rate parameter is represented by the symbol lambda. Now, in order to calculate the rate parameter, we need to know what mu is. In this case, the average. The average is 5 years. Now, the rate parameter, it's 1 over lambda. So that's going to be 1 over 5. 1 divided by 5 is 0.20. And the units is going to be years to the minus 1. So that's how we can calculate the rate parameter. It's very straightforward. Now, part B. Write the probability density function, and then we'll graph it. The probability density function is represented by f of x. And f of x is equal to the rate parameter lambda times e raised to the negative lambda times x. Now, keep in mind, e is a number. It's approximately 2.71828. So now replacing lambda with 0.20, we have the function 0.20 e to the negative 0.20x. And so this right here is the probability density function, or you could say the PDF for short. Let's move on to the left. It is less times laptop. We is just looks like that. Point minus is the this that relating to the and when x was 30,
I don't do it as a percentage, there's a problem. Now, describe for me, how will my calculation, for example, in this, correct? So I want to make an estimate, for example, as to how many people will pay my bills. 50. At the same time, if I, now which do you, he came up with saying that what we have, you'll do it as spam. The mean is 290.
Hello all, my name is
guys.
Krishna. What are we basically going to cover? From basics to advanced. This will be specifically related to positions like data scientist, data analyst, related to business intelligence tool. Everything will get covered. Hello all, my name is. We need to understand the basic differences between have that option. Another -1 is your 7. Bill me. Both the events can topic many people. What? Okay. My base, see what value distribution will be falling here and remaining 20 will be falling here. Isn't distribution. Now you have got a lot of idea about data now. Okay. You just go and search in Wikipedia, see the distribution same. This is also a non-Gaussian distribution. It also follows the Pareto distribution. You can see in this way. Just go and check it out.
Welcome to the closing ceremony of UC Berkeley's AI Hackathon.
And I guess like one thing I wanted to start with is that, just in case you're wondering, this is not normal for AI. I've been in AI for about 15 years, so I can say that with confidence. And but it needs to go into there. Kind of a ChatGPT clone. And this movie takes place in 2035, allegedly, which is 10 years away. And so maybe in 10 years, you can definitely squint and think about that maybe we are going to be in a place where these things are. Hi, everyone. So thank you. It's kind of just like grown together in AI. Tells a workshop of a conference and so say Boltzmann machine, neural network, massive divergence to train your network, and then you're scrutinizing these. That makes any sense because it's been so long ago. Out of proportion, it looks a lot more like this. So this is, I guess, where AI is today, and that's also why this event is so large, I expect. NVIDIA, the manufacturer of GPUs, which is used for all the head and has taken for our neural networks, is now the most valuable company in the United States. We have so many hackathons like this and so on, which I think is maybe are entering the AI field right now. And this is not normal. It's super interesting. I think the nature of computation basically is changing. And we're kind of have like a new computing paradigm that we're entering into. And this is very rare. I kind of almost feel like it's the 1980s of computing all over again. And instead of having a central processing unit that works on instructions over bytes, we have these large language models, which are kind of like the central processing unit working on tokens, which are little string pieces instead. And then in addition to that, we have a context window of tokens instead of a RAM of bytes. And we have later sort of like exciting to a thing, natural interface of like audio, and it sees and hears. This movie, digital space, and physical infrastructure, automating a ton of digital infrastructure. Not just digital infrastructure, but maybe physical, automating a ton of digital infrastructure. Not just digital infrastructure, will probably have its then atoms. But this is another movie that I would definitely point you to. It's one of my favorites. It is not very well known at all. It's called iRobot, and it's from 2004. Will Smith, amazing movie. And it kind of explores this, doesn't go so well. I think it's kind of interesting to think through, allegedly, which is 10 years in a place where the world. And what does that they sort of do? I think the feeling that people talk about is that you really actually continues to work in space. Now, I don't know about you, but I actually find this picture kind of bleak. This is what came out when I put a bunch of the last few minutes of talk into an image generator. And I don't actually like this picture. I think we can do better. And we have a few thousand people here. You're about to enter act I would like sort of power over. So this is humans, animals, and nature coexisting in harmony. But secretly, this is actually a high-tech society. And there are robots and quad in your face over what you want the future to be like. But I don't know about you, but hold it. So maybe we can agree right now that this is better than the previous picture over the last day or two. And the question is, how do we go from hacking to actually change? So what I thought I would do in this talk is go over window into how projects. So sometimes very small projects, like little snowballs, can actually like snowball into really big projects that are sometimes very small projects. Watch. So as an example, I have my fair share of hackathons, like I mentioned. These are some projects from a long time ago that I worked on over the last 15 years or so. So I had a routine, a lot of them. Unsurprisingly, not all of these projects actually go on to snowball. A lot of this is just exploration, your work. It was just like, it didn't add up to and didn't snowball. Tutorials actually ended up snowballing for me in a certain way, because that led me from game programming tutorials to a bunch of Rubik's Cube videos, actually, that became kind of popular at the time. And this kind of sparked an interest in teaching for me. And then when I was a PhD student at Stanford, I got to teach this class, CS231N. And a lot of people have gone on to like this. And this was the first like big deep learning class at Stanford. And a lot of people have gone on to like this. And then after that, I ended up, so a lot of people like that as well. And then on top of that, continuing the snowball, the project I'm currently very interested in is this next class and what it could look like and how I can make it better. And I'm calling that LLM 101N. And it's about building a storyteller, something like kind of a chat GPT that you can work with to generate stories. And about building a story like and how to snowball, the project I'm currently very interested in is this next class and what it could look like and how I can make it better. And I'm calling that LLM 101N. And it's about building a storyteller, something like kind of a chat GPT that you can work with to generate stories. And the idea is you build everything from scratch, from basic prerequisites all the way to like kind of a chat GPT clone in the domain of storytelling. And building that from scratch, I think, will be really instructive, could be really fun. I only published this on GitHub like 2 or 3 days ago, so it's pretty raw and still very much in the early stages, but I'm really excited for it. And this for me is an example of a snowball. It started with like 13 years ago, a little game programming, and I'm working on a course that I think will
I don't like.
Welcome to the closing.
ChatGPT, LLM this, ChatGPT that.
Andre Karparthy, everybody. Thank you, Andre. That was awesome.
Directories, I failed that and didn't know it's a language model and search industry almost. So it was kind of like an interesting setup, I would say. And we were a PhD student at Stanford. I got to teach Stanford, and I'm calling that LLM 101N, and everything from scratch. Building that from scratch, I think, will be really instructive, could be really fun. Excited for it, and this for me is an example of a snowball. It started with like 13 years ago, a little game programming, and I'm working on a course that I think will be really interesting. I think is the snowball that I've witnessed with OpenAI. So as was briefly mentioned, I was a founding member, researcher of OpenAI. And so I was there 7 years ago. These are some images that are public of what it was like working out of Greg's apartment, like 8 of us. And OpenAI was founded to be kind of like a counterbalance to Google. And Google was like this gorilla with 70 billion free cash flow. And back then, Google employed like half of the AI research industry almost. So it was kind of like an interesting setup, I would say. And we were just like 8 people with a laptop. So that was really interesting. And very similar to my background, OpenAI ended up exploring a large number of projects internally. We hired some really good people. And many of them like didn't go too far, but some of them really did work. And so as an example, here's a project that was in an early stage, a very small snowball in the early history of OpenAI. Someone worked on a Reddit chatbot. And if you come by their desk and you're like, what does this look like when someone's working on a Reddit chatbot? We're trying to like compete with Google, and you're working on a Reddit chatbot. Like we should be doing something bigger. And so it's very easy to dismiss these small snowballs because they're so fragile, right? These projects are so fragile in the beginning. But actually this Reddit chatbot, and by the way, don't read too much into the specific details. These are kind of like random screenshots just for illustration. But this was a Reddit chatbot and it looked naive. But actually, Reddit chatbot, what is that? It's a language model. And it happens to be trained on Reddit. But actually, you could train a language model on any arbitrary data, not just Reddit. And when the transformer came out, this was spun into something that worked much better. And then the domain was expanded from just Reddit to many other web pages. And suddenly you get GPT-1, GPT-2, 3, 4, and then you get GPT-4o. So actually, this Reddit chatbot that was so easy to dismiss actually like ended up leading and snowballing into GPT-4o, which we currently think of as this like change in the computing paradigm. And you can talk to it, and it's amazing. So it's really incredible for me to have witnessed some of those, snowballs. And today, OpenAI, of course, is worth maybe somewhere just below $100 billion or something like that. So really incredible to see some of these snowballs in practice. So I would say a lot of you over the last 2 days have also worked on small projects, small snowballs maybe. And it's really incredible to me that some of them probably won't go anywhere, but probably some of them actually will. And you should continue the momentum. The next thing I wanted to briefly talk about is this concept of 10,000 hours that was popularized by Malcolm Gladwell, I think. I actually am quite a big believer in it, and I think that to a very large extent, success comes from just repeated practice and just a huge amount of it. And you should be very willing to put in those 10,000 hours and just literally just count. Don't be too nervous about what am I working about, am I succeeding or failing, etc. Just do simple bean counting of how many hours you're doing, and everything adds up. Even the projects that I failed at and didn't snowball into anything, those add to my counter of the number of hours I've spent developing my expertise and getting into an empowered state of being able to take on these projects with confidence and getting them to work. So a few examples of that. I made this like really janky. I think it still works. I'm not 100% sure. I wouldn't recommend you go there. It's trying to be a movie recommendation engine because I was trying to figure out what to watch on that Saturday. And then I was like, okay, I need to build myself a movie. Wow, that's so cool that you got. It wasn't as amazing to me. And the reason for that was that what this person is not seeing is that this is my 20th time like making a website like this. And so I see all the steps I was going to follow. Okay, I need a Linode, I need a Flask server. I'm going to write some of this JavaScript, style sheets, HTML. I'm going to spin this up together. I need to scrape all these web pages. I need to extract TF IDF vectors. I need to train SVM. And all of these things are things I've already done before 20 times. I already have code snippets lying around from previous projects. And I'm just remixing what I have. And I've already done all of this. And so remixing everything into a new form isn't actually that much work and allowed me to put this up over the weekend. And it's not that crazy. And this only comes from expertise. This only comes from having done it 20 times. So, I was hired to lead the computer vision team at Tesla Autopilot about 7 or 8 years ago. So I was hired to lead the computer vision team at Tesla Autopilot about 7 or 8 years ago. And one of the network training code base in the team was I basically ended up rewriting the computer vision deep learning network training code base from scratch in PyTorch in some of the first few months that I entered the team. And I sort of rewrote the whole thing from scratch. And that ended up being a kernel of what it is now. And I think to some extent, to some people, that looked impressive at the time. But for me, it wasn't because I was coming from my PhD, and I spent 5 years doing stuff like that. And I knew exactly what needs to go into there. I need my training set, my evaluation sets. I need my training loop in PyTorch. I need my configs. I need my log directories. I need to bring in a ResNet. I need to put in detection. We're doing a regression classification. And so the whole thing, like I'm anticipating all the steps. And that only comes from experience. That only comes from having done it 20 times before. And so I think this makes a huge difference. And things that look impressive are maybe much less impressive to you if you've done it 20 times before. So really try to get to this point where you have your 10,000 hours. It makes a huge difference if you've done it 20 times before. Yeah, that's it. By the way, 10,000 hours, if you're doing 6 hours per day, I think this works out to about 5 years. So it's about the length of a PhD that you need to develop expertise in an area. So I think it's roughly correct that that works out to about a PhD length. The other thing that I found is actually quite useful is to keep the dopamine flowing. Be aware of your psychology, your brain, how it works, and what it needs to keep going and how to keep inspired. And so in particular, your brain is a reward machine, and it wants rewards, and you need to give it rewards. So what is a good way to give it rewards? And in my practice, it is by doing projects, and work on projects and continue publishing them. And so here I have a web-page snippet of some of the projects I have worked on in the past. And these are hackathon projects and random projects, and not all of them are good projects. Get you to work on something, stuff, just in case you might wise. Like normally when you go to classes, you're learning in a breathwise fashion. Work on something end-to-end and depth-wise. Like normally when you go to classes, you're learning in a breathwise fashion. You're learning a lot of stuff just in case you might need it in the future. Well, when you're working on a project, you know what you need, and you're learning it on demand, and you're just trying to get it to work. So I think it's people to work on projects. The other thing is putting them up is actually also like a really good Jedi mind trick in my experience. The reason for that is that if you're going to put something up, you're thinking about all the people who are going to be looking at it, your friends and teammates and family and future employers, etc. And so that really increases the bar for your own work. And it makes you work harder because they're going to be looking at it and you feel shame if it was crappy. And so you work much harder and you're going to go that extra mile to make it. You're going to get that reward because they like it, they appreciate it, they fork it, they work on top of it. And so that feels good to your brain. And so the way that this comes together is you are getting your dopamine, you feel good. That way you can build up to 10,000 hours of experience. And that's what helps you a lot snowball your project from a small snowball all the way to a really big one, and actually make change in the world. So in summary, that's, I think, how it works like on a high level. And the message is just keep hacking. That's it. But not the...
Yes, they're ready. The judges will go into... Are you ready?
I started being an entrepreneur around 6 months ago, and we made an AI body cam analysis startup. So I did 100 phone calls, 100 cold calls. I got no clients. 200, 300, 503, and I realized something. The human brain is pretty amazing. We're able to pick up on patterns, but at the same time, it's kind of a single sentence. And we figure out spikes of emotion and decreasing emotions. We see that when we talk about security and data privacy with police officers, it's in our analysis situation. Thank you guys today. I'm open to
competitive. And those teams don't really talk to each other, so maybe it's interesting to think about how do you pull insights from like one channel of sales or marketing and actually bring that into like another channel. So maybe the insights from cold calling are actually influencing what's going on the website. Maybe there's some interesting spots of opportunity there.
Yeah, I could actually talk about one facet of this we want to explore deeply. I want to give you an example. Say we have 3 founders in the company, right? I have a first cold call with one person, and later on, my second co-founder wants to set up a warmer call, right, in the future. And then my third founder wants to set up a third call. We want to build a profile for this client as they go along, so we can truly understand them. And
Hello everyone, this is Siddharthan. In this video, we are going to build a machine learning system that can predict whether a person has diabetes. Or not. Okay, so we will be using one of the important machine learning algorithms, support vector machine. Okay, so we will do our coding in Python, and first of all, let's try to understand about this problem statement, and let's try to understand about this support vector machine algorithm. Then let's get into the coding part.
what's
Support vector machines have a lot of terminology associated with them. Brace yourself. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about support vector machines, and they're going to be clearly explained. Note, this StatQuest assumes that you are already familiar with the trade-off that plagues all of machine learning, the bias-variance trade-off. You should also be familiar with cross-validation. If not, check out the quests. The links are in the description below. Let's start by imagining we measured the mass of a bunch of mice. The red dots represent mice Hurricane Florence came by, filled the sky, but that didn't stop Stat. Josh Starmer and welcome to StatQuest. Today we're going to be talking about some machine learning fundamentals, bias and variance, and they're going to be clearly explained. Imagine we measured the weight and height of a bunch of mice and plotted the data on a graph. Light mice tend to be short, and heavier mice tend to be taller. But after a certain light mice tend to be short, and heavier mice tend to be tall. The data on a graph. Light mice tend to be short, and heavier mice tend to be taller. But after a certain weight, mice don't get any taller, just more obese. Given this data, we would like to predict mouse height given its weight. For example, if you told me your mouse weighed this much, then we might predict that the mouse is this tall. If you told me your mouse weighed this much, then we might predict that the mouse is this tall. Ideally, we would know the exact mathematical formula that describes the relationship between weight and height. But, in this case, we don't know the formula, so we're going to use two machine learning methods to approximate this relationship. However, I'll leave the true relationship curve in the figure for reference. The first thing we do is split the data into two sets, one for training the machine learning algorithms and one for testing them. The blue dots are the training set, and the green dots are the testing set. Here's just the training set. The first machine learning algorithm that we will use is linear regression, aka least squares. Linear regression fits a straight line to the training set. Note, the straight line doesn't have the flexibility to accurately replicate the arc in the true relationship. No matter how we try to fit the line, it will never curve. Thus, the straight line will never capture the true relationship between weight and height, no matter how well we fit it to the training set. The inability for a machine learning method, like linear regression, to capture the true relationship is called bias. Because the straight line can't be curved like the true relationship, it has a relative. The inability for a machine learning method, like linear regression, to capture the true relationship is called bias. Because the straight line can't be curved like the true relationship, it has a relatively large amount of bias. Another machine learning method might fit a squiggly line to the training set. The squiggly line is super flexible and hugs the training set along the arc of the true relationship. Because the squiggly line can handle the arc in the true relationship between weight and height, it has very little bias. We can compare how well the straight line and the squiggly line fit the training set by calculating their sums of squares. In other words, we measure the distances from the fit lines to the data, square them, and add them up. Psst. They are squared so that negative distances do not cancel out positive distances. Notice how the squiggly line fits the data so well that the distances between the line and the data are all zero. In the contest to see whether the straight line fits the training set better than the squiggly line wins. But remember, so far we've only calculated the sums of squares for the training set. We also have a testing set. Now let's calculate the sums of squares for the testing set. In the contest to see whether the straight line fits the testing set better than the squiggly line, the straight line wins. Even though the squiggly line did a great job fitting the training set, it did a terrible job fitting the testing set. In machine learning lingo, the difference in fits between datasets is called variance. In machine learning lingo, the difference in fits between datasets is called variance. The squiggly line has low bias since it is flexible and can adapt to the curve in the relationship between weight and height. But the squiggly line has high variability because it results in vastly different sums of squares for height. The squiggly line has low bias since it is flexible and can adapt to the curve in the relationship between weight and height. But the squiggly line has high variability because it results in vastly different sums of squares for different datasets. In other words, it's hard to predict how well the squiggly line will perform with future datasets. It might do well sometimes, and other times it might do terribly. In contrast, the straight line has relatively high bias since it cannot capture the curve in the relationship between weight and height. But the straight line has relatively low variance, it cannot capture the curve in the relationship between weight. In contrast, the straight line has relatively high bias, since it cannot capture the curve in the relationship between weight and height. But the straight line has relatively low variance, because the sums of squares are very similar for different datasets. In other words, the straight line might only give good predictions and not great predictions, but they will be consistently good predictions. Bam! Oh no! Terminology alert! Because the squiggly line fits the training set really well, but not the testing set, we say that the squiggly line is overfit. In machine learning, the ideal algorithm has low bias and can accurately model the true relationship. And it has low variability by producing consistent predictions across different datasets. This is done by finding the sweet spot between a simple model and a complex model. Oh no, another terminology alert! 3 commonly used methods for finding the sweet spot between simple and complicated models are regularization, boosting, and bagging. The StatQuest on a random forest show an example of bagging in action. And we'll talk about regularization and boosting in future StatQuests. Double bam! StatQuest. Dark clouds fill a graph. Light mice tend to be short, and heavier mice tend to be taller. But after a certain weight, mice don't get any taller, just more obese. Given this data, we would like to predict mouse height given its weight. For example, if you told me your mouse weighed this much, then we might predict that the mouse is this tall. Ideally, we would know the exact mathematical formula that describes the relationship between weight and height. But, in this case, we don't know the formula, so we're going to use 2 machine learning methods to approximate this relationship. However, I'll leave the true relationship curve in the figure for reference. The first thing we do is split the data into 2 sets, one for training the machine learning algorithms and one for testing them. Here's just the training set. The first machine learning algorithm that we will use is linear regression, aka, note, the straight line doesn't have the flexibility to accurately replicate the arc in the true relationship. No matter how we try to fit the line, it will never curve. Thus, the straight line will never capture the true relationship between weight and height, no matter how well we fit it to the training set. The inability for a machine learning method, like linear regression, to capture the true relationship is called bias. Because the straight line can't be curved like the true relationship, it has a relatively large amount of bias. Another machine learning method might fit a squiggly line to the training set. The squiggly line is super flexible and hugs the training set along the arc of the true relationship. Because the squiggly line can handle the arc in the true relationship between weight and height, it has very little bias. We can compare how well the straight line and the squiggly line fit the training set by calculating
Support vector machines have a lot of terminology associated with them. Brace yourself. StatQuest. Hello, I'm Josh Armour and welcome to StatQuest. Today we're going to talk about support vector machines, and they're going to be clearly explained. Note, this StatQuest assumes that you are already familiar with the trade-off that plagues all of machine learning, the bias-variance trade-off. You should also be familiar with cross-validation. If not, check out the quests. The links are in the description below. Let's start by imagining we measured the mass of a bunch of mice. The red dots represent mice that are not obese, and the green dots represent mice that are obese. Based on these observations, we can pick a threshold, and when we get a new observation that has less mass than the threshold, we can classify it as not obese. And when we get a new observation with more mass than the threshold, we can classify it as obese. However, what if we get a new observation here? Because this observation has more mass than the threshold, we classify it as obese. But that doesn't make sense, because it is much closer to the observations that are not obese. So this threshold is pretty lame. Can we do better? Yes. Going back to the original training dataset, we can focus on the observations on the edges, and here we can classify it as obese. However, what if we get a new observation here? Because this observation has more mass than the threshold, we classify it as obese. But that doesn't make sense, because it is much closer to the observations that are not obese. So this threshold is pretty lame. Can we do better? Yes. Going back to the original training dataset, we can focus on the observations on the edges of each cluster, and use the midpoint between them as the threshold. Now, when a new observation falls on the left side of the threshold, it will be closer to the observations that are not obese than it is to the obese observations. So it makes sense to classify this new observation as not obese. Bam! Oh no, it's a terminology alert! The shortest distance between the observations and the threshold is called the margin. Since we put the threshold halfway between these two observations, the distances between the observations and the threshold are the same and both reflect the margin. When the threshold is halfway between the two observations, the margin is as large as it can be. For example, if we move the threshold to the left a little bit, then the distance between the threshold and the observation that is not obese would be smaller, and thus the margin would be smaller than it was before. And if we move the threshold to the right a little bit, then the distance between the obese observation and the threshold would get smaller, and again, the margin would be smaller. When we use the threshold that gives us the largest margin to make classifications, heads up, terminology alert, we are using a maximal margin classifier. BAM? No BAM. Maximal margin classifiers seem pretty cool, but what if our training data looked like this? And we had an outlier observation that was classified as not obese, but was much closer to the obese observations. In this case, the maximum margin classifier would be super close to the obese observations, and really far from the majority of the observations that are not obese. Now, if we got this new observation, we would classify it as not obese, even though most of the not obese observations are much further away than the obese observations. So maximal margin classifiers are super sensitive to outliers in the training data, and that makes them pretty lame. Can we do better? Yes! To make a threshold that is not so sensitive to outliers, we must allow misclassifications. For example, if we put the threshold halfway between these two observations, then we will misclassify this observation. However, now when we get a new observation here, we will classify it as obese. And that makes sense because it is closer to most of the obese observations. Choosing a threshold that allows misclassifications is an example of the bias-variance trade-off that plagues all of machine learning. In other words, before we allowed misclassifications, we picked a threshold that was very sensitive to the training data. It had low bias. And it performed poorly when we got new data. It had high variance. In contrast, when we picked a threshold that was less sensitive to
In machine learning, one of the most fundamental tasks is when you have a bunch of objects that you want to classify into two categories or more. Is this picture of a dog or a cat? Is this dog going up or down? SVMs or support vector machines are some of the simplest and arguably the most elegant methods for classification. Each object we want to classify is represented as a point in an n-dimensional space, and the coordinates of this point are usually called features. SVMs perform the classification task by drawing a hyperplane, that is a line in 2D or a plane in 3D, in such a way that all points of one category are on one side of the hyperplane and all points of the other category are on the other side. And while there could be multiple such hyperplanes, SVM tries to find the one that best separates the two categories, in the sense that it maximizes the distance to points in either category. This distance is called the margin, and the points that fall exactly on the margin are called the supporting vectors. To find this hyperplane in the first place, SVM requires a training set, or a set of points that are already labeled with the correct category. This is why SVM is said to be a supervised learning algorithm. In the background, SVM solves a convex optimization problem that maximizes this margin, and where the constraints say that points of each category should be on the correct side of the hyperplane. In practice, you don't have to worry about the implementation details of this optimization problem. Using SVM can be as simple as loading a Python library, preparing your training data, feeding it to the fit function, and calling predict to assign the correct category to a new object. The biggest pros of SVMs is that they are easy to understand, implement, use, and interpret. Furthermore, they are effective when the size of the training data is small. The simplicity of SVMs can also be a problem. In many applications, the points cannot be separated by hyperplane. A common workaround in this case is to A. Augment the data with some nonlinear features that are computed from the existing ones, B. Find a separating hyperplane in this higher dimensional space, and C. Project back to the original space. A clever technique known as the kernel trick allows us to perform all of these steps in a very efficient manner. And now that you know about SVMs, you can use them for face detection, spam filtering, and text recognition. This was SVM in about 2 minutes. Like and subscribe if you like the video.
Okay, So first of all, let me explain you about the support vector machine model. So this is one of the important algorithms of supervised learning algorithms. Okay, so in supervised learning, we feed the data to our machine learning model, and the machine learning model learns from the data and its respective labels. Okay, so here the labels are the most important things. So what happens is, in this case, we train our model with several medical information such as the blood glucose level and the insulin level of patients, along with whether the person has diabetes or not. So this act as labels whether the that the person is diabetic or non-diabetic. So this will be the label for this case. Okay, so once we feed this data to our support vector machine model, what happens is it tries to plot the data in a graph. Okay, and once it plots the data, it tries to find a hyperplane. So in this image you can see a hyperplane. So what happens is that this hyperplane separates these two data. Okay, so once we feed a new data to this model, so it tries to put that particular data in either of these two groups. Okay, and by that it can predict whether the person will be diabetic or non-diabetic. Okay, so in this case we use several medical information such as BMI of the patient, their blood glucose level, their insulin level, etc. Okay, so now let's try to understand the workflow for this project. So first of all, we need this diabetes data. Okay, so we will try to train our model with the data and the respective labels. Okay, so before feeding this to our model, so there are a lot of steps in between. So we need to pre-process the data, where we will try to analyze the data, and this data won't be very suitable to feed to the machine learning model, and we need to standardize this data because there are a lot of attributes here, a lot of medical information, and we want all this data to be in the same range. So what we do is we try to standardize all this data so that all this data lies in the same range. So all these things will be done in the data pre-processing step. So once we pre-process the data, we will split the data into training and testing data. Okay, so we train our machine learning model with training data, and then we try to find the accuracy score of our model with the help of test data. Okay, so it tells us how well our model is performing. Okay, so once we split the data into training data and testing data, so we will feed this to our support vector machine model. Okay, so we will be using a classifier model, where this model will classify whether the patient has patient is diabetic or non-diabetic. Okay, so once we have trained it, we have a trained support vector machine classifier. So when we give a new data, so it can now predict whether the patient is diabetic or non-diabetic. So this is the workflow we will be following for this project. Okay, so now let's get into the coding part. So we will be doing it in Google Collaboratory. So in our channel, I have already made a video on how you can access Google Collaboratory. from your Google Chrome. So the index of that video is 2.1 and you can search it from there. Okay, first of all. So now we need to import the libraries. So I'll make a text here so that it's clear. Importing the dependencies. Okay. So first let's import numpy. Import numpy as np. Now let's import pandas. So import pandas as pd. Now we need to standardize the data. So for that we need a standardizer function. So from sklearn dot preprocessing import standard scaler. Okay, so this standard scaler will be used to standardize the data to a common range. Okay, from sklearn dot model selection import train test split. So we will use the train test split function to split our data into training data and test data. Okay, from sklearn import svm. So svm stands for support vector machine. Okay, now we need to import the accuracy score from sklearn dot metrics import accuracy score. Okay, so numpy is used to make NumPy arrays. So NumPy arrays are very helpful in our processing. And pandas. So pandas is mainly used for creating data frames. Okay, so it is useful to put our data in a nice structured table. Okay, so then we use this standard scaler to standardize the model, the cell and all. So this dataset is called as PIMA diabetes dataset. So I'll mention it here. So you can also find this dataset in UCI machine learning repository and Kaggle. PIMA diabetes dataset. So you can search in the internet. So okay, now loading the dataset, the diabetes to a pandas data frame. So this week to a options you can give copy path. It's not sure section where you can put in this function is used. So it read a comma separated value. This feature marked with those data frame name, which is diabetes dataset. Okay, so 5 row test case. So you can see the number of pregnancies, the blood glucose level, blood pressure, skin thickness. Okay, so this skin thickness is taken from the triceps. Okay, so this basically tells whether some fat is stored in that particular muscle. Okay, so then we have the serum insulin level. Then we have the body mass index, which is basically calculated by dividing the weight by height square. Okay, and then we have a diabetes pedigree function, which is basically a number which indicates some diabetic value. Okay, and then we have age, and then we have outcome. Okay, so these are the labels. This outcome part is a label where 1 represents that the patient is diabetic and 0 represents that the patient is non-diabetic. Okay, so these are the labels. So all these values will be either 1 or 0. So we need to develop a system that can classify this data to either 1 or 0. Okay, now let's try to see the number of rows and columns for this data set. So I hope everyone of you knows this feature, but I'm just telling this for new users who are just starting to learn Python. So we use hash in Python to write a command. So if I remove this, we have 768 rows and 9 columns. Okay, so 768 columns means 768 rows means we have 768 statistical. Okay, number of use the less than how many outcome value. So I'll run this. As you can see here, so we have 500 values for the label over the. So what's value for this label 0 by. So this will give the mean value for both these cases. So it calculate these values for all the data. The diabetes data set. You diabetic. Okay. Now we can try to get the mean for all those value for this label 0 and 1. Diabetes data set dot group by outcome mean. So this will give the mean value for both these cases. So it calculate these values for all the data set. Let's say, for example, we have this label 0 and 1, and we get that the mean value for glucose for all those people who are non-diabetic is 109, and the mean value of glucose, all those people calculate these values for all the data set. Let's say, for example, we have for both these cases. So it calculate these values for all the data set. Let's say, for example, we have this label 0 and 1. And we get that the mean value for glucose for all those people who are non-diabetic is 109, and the mean value of glucose, all those people who are. So this will give the mean value for both these cases. So it calculate these values for all the data set. Let's say, for example, we have this label 0 and 1, and we get that the mean value for glucose for all those people who are non-diabetic is 109, and the mean value of glucose, all those people who are diabetic is 141. So it is obvious.
And basically train so let's do something like this. So propane belong from. So then we kind of split string x text, y string, and y text. Yeah. Makes sense. So we already have our x and y string. So our model, different result, our model is SVM, support vector machine. No, we have to do, oh shit. You have to standardize first. Standardize standard scalar function. Not this cancel. Why am I putting X tests? This should be my tests.
obvious that the diabetic people have more glucose level in their blood, right? So, and then we have the blood pressure value and all those things. So this difference is very important for us because this is what the machine learning algorithm will see and detect that if a person has these kind of values, they can be diabetic, or if a person has the value in the range of some other value, like say for example 140 or 150, it can predict that that person has diabetes. Okay, so you can also see the age here. So it is obvious that people with more age are more susceptible to get diabetes. So these are some important insights we can get from this data. Okay, so it's a good practice to always group it's up to saying that axis is equal to y because level is around these values. It will standard going to do it. X variable data inconsistent x, okay, standard scalar function, and based on that separately you both guesses it, so that we can here all these values are in the range of 0 and 1. Okay, so this will help our model to make better prediction because all the values are almost in the similar range. Okay, we have already all this did this part here and feeding it to the variable represents the data y. Mention 4 y test from the y is the label. I'll explain the x and all the label. So y. So we have already done this standard. So now so you can. So what these questions is pattern solved as in training but with okay. So basically what we are going to do is we are taking 4 variables. So what these 4 variables means? So we have x train and x test. So this x test. So we will evaluate our that is split y test. Okay. So you and a chance if we don't get a non-diabetic. Let's say for of our x train x, let's check the shape of this function SVM, SVC. So yes, parameter here which is kernel. So using support for this classifier training presents the training much time for training. So if it has trained a training model this label to the word C. All find the training. Okay, so we are prediction now. Okay, beyond 75. So the accuracy change this x-train and x-test y-train. That's what I'm doing here. We have trained our model with the help of this x-train data, test data. So the model very so whether medical 1 represents diabetic patients and 0 represents, as you can see, input data to a numpy array. So this basically is a list. Okay, so list data type, and we are going to change this to a numpy array because the processing on numpy array is more easy and efficient. So we are going to change. So changing the input data to a numpy array. So we have already imported numpy as np as numpy array. Okay, input data as numpy array. So you can follow this same procedure for different projects where you want to make a predictive system. Okay, so this is just like a blueprint. So this will remain almost the same for different predictive systems. So input data as numpy array np.as array. So this function as array will convert this list to an array. So np.as array. So we need to mention this list name, which is input data. So I'm pasting this here. So this will convert this data to a numpy array. Now we need to reshape this data. So reshape the array as we are predicting for one instance. So what is the reason for this reshaping? Okay, so our model is trained on 768 examples, right? So our model is trained on 768 example, and there are totally 8 columns in our model training. But in this case, we are just using one data point. If we don't reshape the array, what the model expects is it expects 768 data points or 768 values, but we are just giving one. So this will make a confusion to the model, and hence we need to reshape the array. And this reshape will tell the model that we are just going to need the prediction for only one data point. So that is the reason for this. So let me create the numpy array named as input one, and it. So this will be .as array. So we need to mention this list name, which is input data. So I'm pasting this here. So this will convert this data to a numpy array. Now we need to reshape this data. So reshape the array as we are predicting for one instance. So what is the reason for this reshaping? Okay, so our model is trained on 768 examples, right? So our model is trained on 768 example, and there are totally 8 columns in our model training. But in this case, we are just using one data point. If we don't reshape the array, what the model expects is it expects 768 data points or 768 values, but we are just giving one. So this will make a confusion to the model, and hence we need to reshape the array, and this reshape will tell the model that we are just going to need the prediction for only one data point. So that is the reason for this. So let me create the numpy array named as input data reshaped. When is the function comma minus thing, we cannot use the raw data as such. Now what we have to do is we have to do the same in the same with the CX to make data. We have made the now let's make the prediction model, and we have stored it in the variable. That variable predict, we have included the label here. Diabetic case to print this predict. Okay, so I made a spelling mistake here. The label for the call is predict. So basically this prediction is why I mentioned inside the index of the value is 0. So case as well, give the predict accuracy file started into training data simple if state diabetic. tell me in the comment. From Google, you can subscribe for more related videos. So this use case or project video will be uploaded on every Friday evening, and you can subscribe for more related video Google Collaborative. Okay. So if you have any doubts, you can tell me in the comments. So you can. Hello everyone, I'm Siddharthan. In this YouTube channel, I teach about artificial intelligence.
Hey there, how's it going everybody? In this series of videos, we're going to be learning how to how to use the matplotlib library in Python. So matplotlib is a plotting library for Python that allows us to create some great looking graphs from our data. So this is used a ton in the data science field and also in applications where we need to visualize our data. So I have the matplotlib website open here, and we can see on their example page that you can make some really nice visualizations using matplotlib. And we'll be learning how to do several of these in this series. So in this video, we're going to be going over the basics of matplotlib and start out with an easy line plot. We'll also learn how to customize the plot style and labels to the axes, add a title, create a legend, and things like that. Now, I'd also like to mention that we do have a sponsor for this series of videos, and we'll talk. So first, we need to install matplotlib. So we can do this easily using pip. So I'm going to open my terminal here, and we can simply install this with a pip install. Now, I have a virtual environment activated. You don't need to be using a virtual environment, but in my opinion, it's always a good idea to create a new environment for when you're starting new projects, even if we're just testing stuff out. Now, if you don't know how to create virtual environments, then I'll leave a link to my video explaining those in the description section below. Okay, so to install matplotlib, we can simply say plot from the matplotlib module. So I'm going to say simple plots to get us started out. So first, I'm going to import pyplot from the matplotlib module. module. So I'm going to say from matplotlib, and we want to import pyplot. And I'm going to import this as PLT. That's a common convention there, to just import that as PLT so that we don't have to write out pyplot every time we want to use that. And now let's create some sample data that we want to plot. So in this video, we're going to add our own data here within Python. And in the next video, we'll see how to read in data from an external source like a CSV file. So I'm going to use some data that I grabbed from the annual Stack Overflow developer survey. They actually just released the 2019 data publicly the day that I was putting this video together. So it was good timing on that part. So the data that I'm going to be using from that survey is the median salary for a developer based on their age. And this is data that I parsed out of the results myself. So I'll be sure to leave a link to my data files here in the description section below for those of you who'd like to follow along. Also, I'm going to make a video in the near future showing how I cleaned and parsed out that data out of their results. But for now, let's just continue on with plotting this. So first, I'm going to create a list, and I'm going to call this dev underscore x. And this will be the values for the x-axis on the plot. And these will be age ranges. Now, I'm a pretty slow typer sometimes, so I'm going to use some snippets here. And again, I'm going to post the link to these snippets in the description section below if anyone wants to grab these themselves. So I'm just going to grab these from my snippets here, just so I don't have to type all these out. So I'm going to grab those and paste those in. And this is just a list here from 25 to 35. Now, in the actual survey, they did actually have all of the ages included, but I didn't want to crowd the screen with data right off the bat. So we're just going to work with a subset of the ages between 25 and 35 for now. But if you stick around to the end of the video, then we'll plot out the median salaries for all of the ages that had enough data. Okay, so now I'm going to create a list, and I'm going to call this dev y. And this will be the values of our y-axis on the plot. And these will be the median salaries for the ages that we added into our other list here. So let me dev y, and this will be the values of our y-axis on the plot. And these will be the median salaries for the ages that we added into our other list here. So let me also grab these from my snippets file. So I'm going to grab those and paste those in. Okay, so now that we have a list of values that we want for our x-axis here as dev x, and a list of values values that we want for our y-axis here as dev y. So now let's plot this. So to plot this data, it's as easy as simply saying plt dot plot. And first we want to pass in the data for our x-axis, which is going to be dev x, and then the data for our y-axis, which is dev y. Now, if you've ever looked at the matplotlib documentation or looked at other examples of people creating plots, then you may have seen them create plots by creating figures and axes and subplots and all kinds of other stuff. And we are going to look at that further on in the series, but we're going to keep it simple now and just use what we have here with plt.plot. So this is going to allow us to work with a single plot, which is perfect for the data that we have right now. So if we were to run this right now, it's not actually going to show us the plot. If we want the plot to show, then we have to say plt.show. And now if we run this, then we can see that we get a very basic plot here. So what this plotted out is a basic plot where we have our ages down here on the x-axis, so between 25 and 35, and those median salaries in that other list are on the y-axis here. So this does make sense to me. It looks like the salaries typically get higher as you get older. So matplotlib comes built in with some nice features, and we can see that this window here has some controls and options down here at the bottom left. So let's go ahead and take a look at some of these. So first, we have a pan to where we can pan around if we want to see anything in particular. We also have a zoom. So if we click on the magnifying glass and we want to zoom in on 26 to 28, then we can do that and then pan around from there. We have the arrows here, and I think these are undo and redo. So if I hit back, then that should take me back to what we did before, and this rezooms and things like that. And finally, we have home here. And also, we have this, which is just more finely detailed zoom configurations here. I hardly ever use that. I usually just use the pan and zoom here. And lastly, we can save that if to work with a single plot. At the show, you can see that we get the x-axis, so between 20 basic plot here. So what this plotted out is a basic plot where we have our ages down here on the x-axis, so between 25 and 35, and those median salaries in that other list are on the y-axis here. So this does make sense to me. It looks like the salaries typically get higher as you get older. So matplotlib comes built in with some nice features, and we can see that this window here has some controls and options down here at the bottom left. So let's go ahead and take a look at some of these. So first, we have a pan to where we can pan around if we want to see anything in particular. We also have a zoom. So if we click on the magnifying glass and we want to zoom in on 26 to 28, then we can do that and then pan around from there. We have the arrows here, and I think these are undo and redo. So if I hit back, then that should take me back to what we did before, and this rezooms and things like that. And finally, we have home here. And also, we have this, which is just more finely detailed zoom configurations here. I hardly ever use that. I usually just use the pan and zoom here. And lastly, we can save this and pan around from there. We have the arrows here, and I think these are undo and redo. So if I hit back, then that should take me back to what we did before, and this rezooms and things like that. And finally, we salaries in that other list are on the y-axis here. So this does make sense to me. It looks like the salaries typically get higher as you get older. So matplotlib comes built in with some nice features, and we can see that this window here has some controls and options down here at the bottom left. So let's go ahead and take a look at some of these. So first, we have a pan to where we can pan around if we want to see anything in particular. We also have a zoom. So if we click on the magnifying glass and we want to zoom in on 26 to 28, then we can do that and then pan around from there. We have the arrows here, and I think these are undo and redo. So if I hit back, then that should take me back to what we did before, and this rezooms and things like that. And finally, we have home here. And also, we have this, which is just more finely detailed zoom configurations here. Finally, we have home here. And also, we have this, which is just more finely detailed zoom configurations here. I hardly ever use that. I usually just use the pan and zoom here. And lastly, we can save this. So if I wanted to save this as a PNG, then I could click that and save this plot as a PNG file. So that's a quick little overview of this window here. Okay, so now let me close this down. And now let's look at how to add some more information to our plot. So right now, there's no way to actually tell what that data represents. If we were to send this to somebody, or if we were to look at this ourselves, then no one would actually know what that X and that Y axis were supposed to be. There's There's no labels or anything like that. Now, the point of these plots is to visualize the data in the easiest to digest format as possible and relay the information that could just get hidden in the numbers. So we need to have some labels here to show what this actually represents. So first, let's give our entire plot a title. So to do this, I'm going to do this right above plot.show. I'm going to say plt.title, and let's pass in a title of median salary, and then I'll say that the salary is in USD by age, okay? And now to label our X and Y axis, it's as easy as saying plt.x label, and we want our X label to be ages, and right below that, I'm going to say Y label, and that Y label, let's say median salary, and again, we will specify USD. Okay, so now if we run what we have here, then now our plot is a little bit more detailed. So now we have some more useful information here. So we have a plot title up here at the top that tells us what this chart is about, and our X and our Y axis now have labels explaining those as well. Okay, so now let's add another line to our plot. So let's say that I wanted to also plot the median salaries by age for Python developers specifically. So the values that we have right now are for developers of any language. So now let's do Python. So to do this, we can simply create more lists and plot just like we did the first ones here. So let me close this down. So I grabbed that data from the Stack Overflow survey as well, and I added those to my snippets also. So let me grab those from the snippets, and those are right here, median Python developer salaries by age. So I'm going to grab this PyDev X and this PyDev Y. So I'm going to go back to my script here, and right below my other data, right below where I'm running plt.plot of that other data, I'm going to paste this PyDev data in, and now I can plot those simply by saying plt.plot, and now we want to pass in PyDev X, and we want to pass in PyDev Y. Let me get some spacing there. So now, if I were to actually run this right now, then that would work. But before I do that, if we look at our x-axis here, then we are just repeating those same age ranges from the other list. So we have 25 to 35. So instead of repeating these in both of our plots, let's just rename our x values at the top here and use that for both plots. So instead of devx and pydevx, I'm going to just remove that pydevx there. And now this X list here at the top, I'm going to rename this to ages underscore X, and now I'm going to use that for both plots. So I'm going to use it in my first plot there and replace devx, and in the second plot, I'm going to replace that pydevx. So now we're using this same data for our x-axis, and the y-axis, we are plotting different data. So like I said, we could have had that repeated list in there and it would have worked just fine, but this is just a way of cutting down on repeated code. Okay, so now if we run this, let me go ahead and make that output a little smaller there since we're not using that. So now if I run this, then we can see that now we are getting 2 lines. So that's nice, but we don't know which line is which. So we need to add a legend to tell us which line represents what data. So let me close this. Plot here. And there are 2 ways of adding legends. So the first way is to do it like this. I could add labels for the legend as a list of values in the order that they were added to the plot. So down here at the bottom, actually, let me actually put this below the title here. So I could say plt.legend. And now we can pass in a list of values in the order that they were added to the plot. So our all of our developers, this dev y was added to our plot first, where we did plt.plot, and the Python developers was added second. So plt.plot here with pydev y. So I could pass in a list and just say all devs is the first value, and Python is the second value. And if I run this, then we can see that that works. We get a plot, and the legend is telling us which line is which here. But there's a way that I actually like to do legends that I really think is better than this. So let me close down this plot here. Now, I don't really like this method of adding legends because you have to know the order that all of these things were added to the plot. And I feel like that's extremely error prone. So I think that this is a better way to do it. So we can pass a label argument to our plot methods. So instead, let me copy this part here where I said all devs. Instead, up here where we did our first plot, I can pass in a label argument and say label is equal to all devs for that one. And for the second plot, I can say label is equal to, and this will be Python. And now when we actually run this legend method here, we can actually do that without any arguments. So I'm just going to leave that empty. And now it's just going to use these plot labels instead. So now if I run this, then we can see that that works. But I feel like this is a lot less error prone and easier to read. And it also kind of self-documents our code as well. If we look back here at the code, then we can see that this is self-documenting in a way where it's telling us what we're actually plotting here. So I think that that's a much better way to do it. Okay, so now that we have those plotted, let's look a bit at how we can change some of the formatting of this plot. So let's say that I wanted some different colors and styles for the lines and things like that. I feel like since one line is just developers in general, I'm just going to make that line gray, and we'll make the Python line blue since that's one of the main colors in the Python logo. Now, there's a way to pass all of this information in all at once, but I hardly ever do it this way just because I think it's hard to read. So I'll show you a quick example just in case you see this in someone else's code, but then I'll show you how I normally do it as well. So we could pass in all of the information at once by passing in a format string after our y values in our plot method. So let me pull up a web page here and show you what this format string actually expects. So, whoops, and I did have it pulled up here, but I may have overwritten it here. So let me see. Okay, here we are, format strings. And let me make this just a little bit larger here so that everybody can see. So we can see here that it says that a format string consists of a part for color, marker, and a line. So format string looks like this: marker, line, color. So let's say that for our line graph, we wanted a black dashed line. So to do that, we can scroll down here. These are the marker styles. We're not using markers right now. We're using lines. So I'm going to go down to the line styles. So we can see that just a single dash here is a solid line style. A dash dash is a dash line style. So that's what I'm going to use. But then they also have a couple of others here. Now, let's also look at the colors here. So these are the general colors. So B is blue. So if I wanted black, then that is K. So if I go back up to our format string here, then it says that, let's see here. Yeah, so if I go up here, yeah, so color, marker, line. Okay, so now let's go back to our code here. And now let's pass in a format string after our Y value. So I'm going to say that I want this one to be black, so that was K, and then dash dash is the dash line. So for Python, if I wanted this one to be blue, then I could just pass in a B for blue, and then I'll leave everything else as the default. Since a solid line is the default, we don't have to change anything there. So now, if I save that and run it, then we can see that now our line with all of our developers is this dashed black line here, and our Python line is this blue line. So we're able to change that up a little bit. Now, like I said, I've never really liked these format strings that contain the colors and the marker styles and the line styles all in one, because I don't feel like that's liked these format strings that contain the colors and the marker styles and the line styles all in one, because I don't feel like that's very readable. I always forget how to write these down and what these are supposed to be. So I just wanted to show you these in case you saw them in someone else's code, but I prefer to be more explicit and make our code a bit more readable. So to do that, we can pass these in as arguments instead. So instead of doing it this way, I'm going to say that color is equal to K, and then I will say line style is equal to dash dash. Now that's a little harder, or that's a little more code there, but I think that that is much easier to read. So also down here in the Python plot, I'm going to say color is equal to B, so for blue, and that should work exactly the same as our format string worked, but in my opinion, it's just more obvious what's going on there. So if we run that, then we can see that we get the exact same results there. Now, if you also wanted to add markers to your lines, then we can do that as well. To do that, we could simply say, so after line style here, I'm going to say marker is equal to. And if you want to know what marker styles you can use, you can go back to that formatting page where I showed all those different formatting options. But I know that some of these off the top of my head, I know that the dot is one, and let me also put one in here for Python as well. And I know that circle will do like a larger marker there. So now if I save that and run it, then we can see that now these have markers here. So we have these small markers for all developers and these bigger markers for Python. And I'll be sure to add a link in the description section below to that formatting page in case you want to check out more options that you have here. Now, I don't really like these markers on this specific chart. So I'm going to go ahead and go back and just undo a couple of steps here before we put those markers in. Okay, so we can also use hex color values for our lines as well. And that's normally what I use since you have a lot more color options and it's easier to find color palettes online that look good and contain those hex values. So I have some written down here that I'm going to use for our plots. So for the developers line, I'm just going to use a hex value here. So for color, I'm just going to use a hex value of 444444. And if you don't know how hex values work, the first pair of numbers are going to be for the red values. The next two numbers are going to be for the green values. And the last two numbers are going to be for the blue values. So with all those being the same, it's going to generate a shade of gray. And this is a darker shade of gray. And you can find hex color palettes online if you'd like like to come up with some of your own. Now for Python, I'm going to set this to this steel blue color that I found online. So I'm going to change this to be a hex value of 5A7D9A. And just to show one more line of information and colors here, let me also add in some JavaScript data that I have here in my snippets as well. So I'm going to go back to the snippets. And now, since we're sharing the X, we can just copy the Y values that I want here. So I'm going to copy these Y values, and these are the median JavaScript developer salaries by age. And underneath our Python data, I'm going to paste that in. And let me actually get this plotting data here beside what it's actually plotting there, okay? And now let me copy the Python line here, and I'm just going to use that for my JavaScript data. But instead of plotting the pi dev y, I'm going to plot the JS dev y. For the color, I'm going to change this to a yellowish color. So this will be AD, AD3B, and for the label, I'm going to say JavaScript. Okay, so if we run this, then we can see that now we get 3 lines here on our plot. All of them have labels and legends, and they all have their own customized colors and styles as well. So that looks pretty good. Now, I'm not sure why the Python developers in the survey are reporting higher salaries like this. I didn't expect it to be that much of a difference between the different types of developers, but that's just what was in the data. Now, I feel like these lines are a little bit thin right now. So let's say that we wanted the lines for the specific languages to be a little bit wider so that they're more emphasized and just keep general developers as it is. So to do that, we can add another argument to both of our plot methods here. And to make these lines a little thicker, I can just say line width is equal to, and I think the default is 1. So let's try 3 and see what this looks like. Like. So I'll do that with both Python and JavaScript, and I'm going to leave the all developers as it is. Now this could actually cover up our dotted line because lines are layered in the order that they're added. So instead, I'm going to move our dotted line to the bottom here. So I'm going to grab this plot and grab this data, and I'm going to move that to the bottom so that it's plotted on top, just in case it would have been hidden behind any of those other 2 lines. So do you remember earlier when we changed our legend to use these labels instead of passing them directly into our legend method? Well, this is why that was a good idea, because moving the plotting order like we did just now would have meant that we needed to manually come down here and change the order that we passed in those legends also. And if we forgot that, then our plot would just be wrong. But since we did it this way by using these labels instead, that just updates automatically. So that's why I prefer that method. So let's go ahead and run what we have here, and we can see that now our language lines are a bit thicker, but we can still see that all developers line over top of the JavaScript line here where it would have been hidden behind. Okay, so that looks pretty good. Now I'm on a larger monitor here, but whenever I was running this on my laptop, I noticed some weird padding issues. If you ever notice that your padding isn't very good and that stuff is getting cut off, then there's a way that we can take care of that. And let me go back to the code here. And to take care of that, I'm just going to do this right above plt.show. To do this, I'm going to add in a line that automatically adjusts our plot parameters to give some padding. And to do this, it is just plt .height underscore layout, and that is a method. So if I run this now, then it kind of looks the same on my machine, but on my laptop, it made the padding a lot better whenever I ran that. Now, there's one more thing about the plot that I think that we could improve here. Now, if we look at this, if we go out here further to the right, it might be harder to tell when we cross certain salaries. So if we put in a grid, then I think it would make this a lot easier to read. So if we go back to our code, we can put in a grid really easily just by saying, and I'll just do this above where we currently are, I'll just say plt.grid, and we just have to pass in a value of true. So if we run that, then now we can see we have a grid. So we can tell exactly when each of these lines crosses certain salaries and ages here. Okay, so that's looking pretty good. Now, one more thing before we finish, let's look at how we can change the style of our plots and make these look a bit better. Now, we have some built-in styles that we can use with Matplotlib. So let me go to the top of our file here and let's use some of these here. So underneath our imports, I'm going to say plt.style. And to see the available styles that we can use, we can access a list of available styles by saying plt.style.available. Now, that's not a method, so you don't want to put in parentheses there. It's just an attribute, so don't execute that. So now let's print that out to see what styles we have available. And I'm going to comment out our plt.show so that a plot doesn't show up when we run this. So I'm going to run this, and I'm going to make our output a little bigger here so that we can see these. And these are the available styles that we can use that are built into Matplotlib. And you can experiment around with these and see which ones you like. Personally, I really like the 538 style, and I also like the Seaborn and the ggplot styles. And I'll probably use a few of those throughout the series. Just so we can get an idea of what some of these different styles looks like. So let's say that I wanted to use the 538 style. So to do this, I could simply say, I'm going to overwrite our print statement here. I'm going to say plt.style.use and then pass in the string of 538. So now let me uncomment out plt.show and let me run this. So when I run this, I don't know if you remembered what that looked like before, but now this is a bit of a different style. And these styles all have their own unique way of coloring lines and stuff like that. Too. So you could also try plotting these without your custom colors and see if you like the style's default colors more than the ones that we specifically added for our lines. So I'm actually going to try that. I'm going to remove my colors and line widths for Python and JavaScript plots, and I'll just leave the all devs plot as it is. So for Python and JavaScript, I'm going to remove the line width and I'm going to remove the color, and I'll do that for JavaScript as well. And let me make this output a little smaller here. And I'm also going to remove the grid as well, since some of these styles also have their own grid preferences as well. So I'm going to remove that. Okay, so now with all those in place, first, let me comment out where I'm using the style and run that plot. So that is the default Matplotlib style. And now let me plot with the 538. So if I look at both of these, then you can see the difference here. There is a definitely a different style with the 538 plot over here. And I really like the 538 default colors and styles here. Now, if you want to play around with different styles, then it's as easy as choosing another one from the list that we printed out just a second ago. So if I wanted to try a ggplot style instead, then I could just say .use ggplot. If I run that, then we can see that now we get a different looking style. And this one kind of has like a grayish background with some thinner lines here. Now, speaking of styles, let me show you something else that I think is pretty cool that's built into Matplotlib. And it's nice if you have like a blog or something where you're making some plots and want to have a little bit of fun with it. Now, most of you have probably heard of XKCD Comics. They publish some online comics that are usually pretty funny, and a lot of those are tech related also. For those of you that have watched my videos in the past, then you might know that the Python has a standard library module called anti-gravity, and it actually opens up one of their comics in the browser. Anyways, they have a pretty distinct style with their comics, and Matplotlib actually has a method that will mimic the style of their comics, and it's super easy to use. So in order to use that, all we'd have to do, I'm going to overwrite this style line here. Now, this is actually a method instead of a style. So this will be plt.xkcd, and that is a method. And with that small change in place, if I run this and make this a little larger, then now you can see that this is kind of
Oh, here it goes. SKCD. Oh.
ed, and that is a method. And with that small change in place, if I run this and make this a little larger, then now you can see that this is kind of in the style of those XKCD comics. So it kind of looks like a graph that you would see embedded in a comic somewhere. It's kind of got these squiggly lines here that kind of makes it look like it was hand drawn by somebody. So I think that's a pretty cool built-in feature that Matplotlib has, and it's a fun way to mix up your plots if you're making them for something that isn't too serious. So if you wanted to actually put this on your website or something, then you could just save this as a PNG like we saw before and then upload it that way. Now, we saw how to do that here within the window, but we can also do this programmatically as well. So if I close this plot here, if we go back to the code, I'm just going to save this right here before plt.show. In order to save this as a PNG, then we can simply say plt.savefig. And now I'm going to just save that as plot.png or something like that. And that will save an image called plot.png to my current directory. Now, if I wanted to save it somewhere else, then you can also pass in a full path here as well, and it'll save it to whatever path you pass in. So I'm going to run this, and it's going to show that graph there. But if I open up my current directory, we can see that I have a plot.png here. And if I open that, then we can see that it saved that PNG file here in my directory. Okay, so real quick, let me do one more thing before we finish up here. So I mentioned towards the beginning of the video that I'd plot the data for ages of 18 to 55. That's the larger set of data that they had in the survey, if anyone was interested in seeing that. Now, I didn't do it earlier because I didn't want to crowd the screen with tons of data, but let me grab that from my snippets file and see what this looks like. So here within the snippets, these are all of the ages that had enough data here. They had more data ages than this, but these were the only ones that had, I think it was like over 100 answers to the question or something like that. I can't remember exactly the cutoff that I used there, but it was something like that. There were some people who, in their 80s and 90s that answered the survey, but there were so few of them that it was hard to get a mean that was trustworthy. So these are the ones that had, hundreds of answers. So lastly, let me grab this last list here. This will be the last one that I need to replace. And again, these will be available for download on my GitHub page if anybody else wants to follow along. So now that we have all that data copied and pasted into our script, now let me save that and run it. And now this is the data for all of those ages and the median salaries. So it looks like that big gap between Python developers and other developers was mainly between the ages of 25 and 35. That's what we saw here. And once we plot the rest of these, then they're a bit more in line. The other languages catch up around in here, and Python doesn't have such a big gap anymore. But it still looks like Python does have the leverage here in most of these ages, though. Okay, so before we end here, I'd like to also mention the sponsor of this video, and that is Brilliant.org. So in this series, we've been learning about matplotlib and how to plot data in Python, and Brilliant would be an excellent way to supplement what you learn here with their hands-on courses. They have some excellent courses covering the fundamentals of statistics,